unfortunately. So let us begin with computer science. In other disciplines, there's one discipline I haven't talked about yet. We talked about social science and art, medicine and science, cool stuff. They take my computer science degrees away if I didn't talk about cryptocurrency. That's another thing that everybody is up in arms about. I guess it's kind of died down a little bit, I would say, but it's still a thing. People are still out there buying Bitcoin and things like that. So let's talk about that and try to understand it. Like, how does it work? What's in it for me? So yeah, I'm going to focus on Bitcoin for this little subsection of the day. That's just like, it's the most popular one, so might as well. There are others though, like Ethereum, plenty of other, they all have their logos of course, but Bitcoin's the most popular one, so let's talk about that. And I'm not going to get down into the nitty-gritty details too much, but I'll get close. But yeah, at the start, what is a cryptocurrency in general? It's money. People are using it to exchange things, to buy things. It's a kind of money that is completely electronic. There's no paper bills or anything like that. The way it works is it uses encryption. It uses properties of encryption to make sure that, like, first of all, nobody can take your stuff. Like, your stuff is yours only. Your money, your Bitcoins are only yours. And then also it makes sure that, like, you're just a number. You're just an account number, and nobody knows who you are until you cash out. Convert your stuff back to dollars or something. At that point, then whatever service you use needs to alert the IRS, and then you have to pay taxes and stuff. But until then, you're good to go. Okay, so yeah, uses encryption. It's wonderful. RSA is the kind of encryption that is the backbone of it. We've learned a little bit about that. But it was made back in 2009, and oh man, I wish I bought Bitcoin around then, by somebody named, like, they published a paper and their name was Satoshi Nakamoto, but this is not a real person. So whoever this was, their name really wasn't Satoshi Nakamoto. It's a pseudonym. It's a fake name. People have some guesses as to who the author of that Bitcoin paper was, but we're not sure. Okay, so yeah, the idea of a cryptocurrency is, it's like everybody has an account. Like, I have an account maybe, and then, like, my cat can have an account, and all these are just numbers. Like, I have an account number in the Bitcoin network. It's just a bunch of ones and zeros in binary somehow. Like, my cat has an account number in the Bitcoin network, and I have a couple Bitcoin, and the goal is, like, I would like to give my cat Bitcoin. All it is, it's like you're transmitting information across the network, and then everybody's agreeing. So I'll talk about that. Like, I want to give up my Bitcoin. There's some nice algorithm that makes sure that, like, when I pay my cat money, the money goes away from me and gets placed into my cat's account. Okay, that's the idea. So hopefully that makes sense, because, like, you can't duplicate money. That would be a bad thing. It has to go somewhere and stay there. So properties of encryption are nice there. But yeah, they're really hard to track because it's just numbers at the end of the day. Like, nobody knows whose number is who for Bitcoin, whose account number belongs to whom. The only time people know is when you start exchanging it for, like, dollars, for, like, real world currency. Because at that point, like, somebody has to pay taxes. So that's interesting. And yeah, so all of these are called wallets in the Bitcoin terminology. Everybody has a wallet, and really that's just an account number. In the Bitcoin network, we call those, like, addresses. That's your account number. So those are, like, the same word. They're synonyms in the cryptocurrency field. And yeah, Bitcoin's the most popular one, but plenty, thousands, maybe even more. Maybe we're getting close to 1 million now. Who knows? You can make your own altcoin if you want. Alternative Bitcoin. Okay? But nobody's as cool yet. Everybody loves Bitcoin. So, yeah. Feel free to shout out if you have any comments or questions about this stuff. It's an interesting idea. All right? And people are crazy about it. So let's talk about a piece of the Bitcoin protocol. It's called the blockchain, piece of the network. So Bitcoin is a bunch of computers connected to each other. The Bitcoin network, we say, It's a peer-to-peer network, so it's like you're sharing files. It really is sharing files, essentially. It's a network of computers working together, trying to like agree on who has what in their accounts. So, like, it really is just a bunch of servers sitting around. They're all connected to each other, and I could be a part of the Bitcoin network if I wanted to. I could put my laptop on it. I think some students once, they used some of these computers to mine Bitcoin. Please don't do that, you'll get in trouble, but that was funny when I learned that. But yeah, I could connect my own laptop to the Bitcoin network, and it could be a piece of it. But it's just a bunch of computers, they're all agreeing on things, and it's powered by encryption. So like everybody's account number, it's back to this idea of RSA, which had a public key and a private key. So your account number is essentially your public key, the thing that you're telling to everybody. Like, all right, this is me, this is my account, and like you can host it over here. And it's only yours, Lawton's account. So I know my account number, it's my public key, and everybody gets to know it if they want to pay me. That's the whole point. And if I want to send somebody else money, I'll give my money into the network, and I'll send it to somebody else's public key. That's their account number. But then I keep my little private key very secret and close to me. My private key is what's unlocking my account and allows me to send money, actually have access to it. So that's the whole point. The power of RSA, lovely, lovely encryption. But yeah, the idea of this network is that everybody is connected. All these computers are connected. Millions of computers are connected to the Bitcoin network, and they're all trying to agree on who has what. And there is a file, just a special big long file called the blockchain. And this is how everybody agrees. There is a file that everybody has, and it's called the blockchain. And what is on it is every single transaction that has ever been made on the Bitcoin network. Do you see how if everybody had this file, you'd know which account has what, because you just replay the entire blockchain. And you know exactly who has how much money, how many Bitcoins. So everybody has a copy of this file. And essentially, like I'd have my own copy if I put my computer on the Bitcoin network. The idea of spending money is writing to the blockchain and telling the network about it. And then everybody agrees, like, oh yeah, that is a valid transaction. Okay, so that's the idea. So like if you read it in order, you know exactly which accounts have how much money. That way, you're like, you know that somebody has the Bitcoins if they want to spend it. I can't just be like, my empty account sends 42 Bitcoins to my cat's account. Like nobody's going to agree on that because they're all looking at the blockchain and they're like, you're crazy. That's not happening. We're not allowing that. Okay, so like everybody on the network has their own copy of the blockchain, and they all keep it in sync. Okay, so whenever somebody spends their Bitcoins, like if I send one of my $signs onto the network, then everybody's copy of the Bitcoin blockchain gets a copy of that transaction added to the end of it. And everybody has to agree, like I had that money, I sent it to that address, everybody agrees that that transaction took place, and that's how it all works. Through public keys are my addresses, or my account numbers, and private keys are how I unlock my account, like my password. So, yeah, that's the idea. You may, and there is a way to break Bitcoin. There's a way to spend 42 Bitcoins when you don't have 42 Bitcoins, but it'll never happen because of strength in numbers. All right, so if you are a bad person, of course you're going to want to write to the blockchain saying, like, my account gets 1,000 Bitcoins from this other account. But it's not going to work out because there are millions of computers connected on this network. All right, millions upon millions of computers. And they all have to agree, and you, maybe you control a few computers, but you don't control the majority of them. Okay, that's the secret. Here's all the computers on the network. Like maybe you're a hacker and you're able to take control of this much of the Bitcoin network somehow, but you got plenty more guys over here who don't trust your fake transactions. Okay, so yeah, greater than 50% of the computers connected to the Bitcoin network currently have to agree in order for some transaction to happen. In order for like me to spend my money, everybody has to agree on it. At least half of the network has to agree on it. Okay, so there is a way to take over Bitcoin and render it useless and like make Bitcoin out of thin air, or put somebody else's Bitcoins into your account. If you had like a lot of computational power. Like if you used all the supercomputers for every country ever, all their firepower, then you could technically make Bitcoin whatever you want it to be. You just need control over 51% of the network. That's very hard to get, though. Okay, so that's why people trust Bitcoins, because there's so many just people on the network and nobody agrees. Nobody's like in cahoots. They're all just separate entities, and so that's what makes it strong. Strength in numbers. Okay, they're all going to agree only if it's a valid transaction, which is nice. But a lot of alternative Bitcoins, altcoins, they have been taken over because not a lot of people are on that alternative Bitcoin network, and it wasn't too hard to buy a few servers in the cloud and take it over. So that's why people flock to Bitcoin, is because of all the people on it. It just gets stronger that way. That's kind of cool to think about. And so there is one way to generate Bitcoin out of thin air that you've probably heard of. That is a valid way that people agree on. It's called mining Bitcoin. It's an incentive. All right, so let's talk about that, because I'm sure you've heard that term before. So what mining is, as far as Bitcoin is concerned, it's an incentive. That's the key. It's an incentive for people to put their computers on this network. Like, it costs money and electricity to be on the Bitcoin network. It costs money in internet, right? So why should you be on the Bitcoin network? Because you can make Bitcoin out of thin air. Here's how you do it. All right, so it's an incentive for people to put their computers on the network and keep a big long copy of that blockchain. Like, you need a lot of storage space, right? What happens is every time a few transactions go through in the Bitcoin network, a lottery happens. So there's a little lottery, and all these computers are taking place, all the ones that are approving these transactions, every couple transactions. The idea is one of the players that was approving that transaction, like going through their blockchain, making sure it's okay, and just like sending that information out to the network. An incentive for doing that is that one lucky participant in the network gets a Bitcoin, or a fraction of a Bitcoin. So it gets generated out of thin air, and it goes to the lottery winner, somebody who helped out in that transaction, helped out approving. Okay, so that's essentially how money is getting printed in Bitcoin. That's how new Bitcoins come to light. Okay, and yeah, so the secret is it's really everybody's just solving a math problem really fast. That's how Bitcoin gets generated. That's how you verify transactions. The secret is, like, a bunch of computers, they're all working, and the Bitcoin network is like, all right, to approve this transaction, you need to make a number that combines all of those transactions. You need to make a secret number that combines all the transactions and then also starts with a certain number of zeros, and it's an encryption process. So it's hard to come up with a number that has this many zeros at the front by random. And so they just keep trying numbers, solving a math problem really fast. That's what all the computers are doing, trying to approve the transaction, put a number here and a bunch of zeros here. That's pretty much it. And they have to come up with the number in a special way. It has to be reproducible. So that's essentially all Bitcoin mining is. It's just solving a math problem very fast. And then the first person who gets the answer right gets the new Bitcoins. And so yeah, that's how money gets printed. Eventually, the supply of new Bitcoin during mining will taper off. It's already started. So at the start of time, when Bitcoin first started, a lot of Bitcoin were generated when you approved a transaction and you mine stuff. But slowly but surely, there's an exponential decay going on, and over time, fewer and fewer Bitcoins are being generated every transaction. Okay? Trying to curb inflation or something, I don't know. But one day, a few decades from now, that will go to zero. So you get nothing. There is no incentive at that point to approve of Bitcoin transactions. And the hope is that the transaction fees that you have to pay to the computers every time they approve something will take over and be enough. But that's eventually the future. Eventually, mining will not be a thing in the Bitcoin network. It's already not very profitable. A lot of people switch to like mining Ethereum or other things. So that's why we have GPUs able to buy these days, thanks to Bitcoin mining not being as lucrative as it used to be, because that supply is tapering off. That's just the algorithm. That's how it's doing it. Does that make enough sense? It's a weird idea. Like, you win you do a math problem quickly enough, you get some Bitcoin, and then it's just like you send your virtual money to somebody else's number that represents their account. very odd. Just a bunch of computers connected to each other, sharing a file, using up a lot of electricity. So we should ask ourselves, this is like an ethical question. A lot of people disagree with Bitcoin. And by the way, here are the prices of all the Bitcoins every time I've taught the class. So like the first semester, like almost 4 years ago now, I taught the class. Like that was its price. Then it shot up real quick. Then it got to here. And then that's the order. And right now, this is where it's at. This is its current price. So it's almost hit the peak from, I guess, what was this? Fall of 2021 when I taught the class. So it's getting there. But yeah, is this okay? Is it okay to have Bitcoin, to have cryptocurrency? Because first of all, like the first uses of Bitcoin, by the way, is like nobody in real life is letting you buy, like Trader Joe's isn't letting you buy your groceries with Bitcoin these days, right? The first uses of Bitcoin, and still to this day, a lot of uses of Bitcoin are places where you will want to remain anonymous because that's something Bitcoin enables. It would be like a black market. People are buying drugs with Bitcoin. The idea. So that's a bad thing. That's a con for sure. And then also, like governments, they can't track who owns what. And so that's another, like if you want to be utilitarian about it, we can ask our boys, of course. But like if you want to be a utilitarian about it, like maybe it's good that the government doesn't know whose account number is what on the Bitcoin network. But it's bad for them for tax purposes. Like you'd have to weigh that. So yeah. Also, this exchange rate, Bitcoin is for all intents and purposes, it's gambling. It's just like stock market stuff. It's got an exchange rate that's not really pegged to anything. There's no real guarantees that the Bitcoin you buy today will be worth anything tomorrow. Like there are ups and downs, as you can see from these charts. Okay, so yeah, so no real governments these days are like, yeah, we're getting behind Bitcoin. Some governments have made their own alternative cryptocurrencies. That is a thing, but that's not really been popular. So, is it okay? Should this be allowed? Should people have cryptocurrency? Because it's like there's pros and cons. So let's talk about what Kant might think. What would a deontological ethical theorist think? Well, Kant's always about the word always. So let's ask the question. Let's frame it in terms of what he might think. So like Kant would. He's totally for individual rights, so he's like, I like to be separate. I don't want the government to like be peering into me. Like I want to have my privacy. So he'd probably be like, yeah, people will always naturally pay their taxes, right? That's what you're supposed to do. People should always pay their taxes because that gives you good stuff from the government and like keeps your society working. So he trusts people enough to be like, yeah, I think people should be able to have cryptocurrencies if they want to. I think Kant would be a proponent. And then a utilitarian like Mill, what would he say? Then you do your weighing game. Like from the government's point of view, cryptocurrency is more or less bad. It's unless they start regulating it more heavily. Like you get less tax money when money floats around between people in the Bitcoin network. Like you don't have to pay taxes because nobody can track where you are. There's a lot more illicit activity because you don't have to put a name to an account number. It's just a number. And then also, I didn't talk about this yet, but like there's probably over 1 million computers probably on the Bitcoin network. I haven't kept track, but there is a giant environmental cost. The last I heard, just the amount of energy expended just to take part in the Bitcoin network is at the scale of how much energy is used by Argentina. So that's how much energy it costs to use Bitcoin, and that's horrible for like the health of this planet, right? So that's not good. And so those are huge downsides that you would have to take into consideration if you're a utilitarian. And then also, on the flip side, though, it's great for individual freedom. Like I'm not being tracked when I use Bitcoin, which is nice. That's a good thing, and privacy is important, and you have to weigh that into your giant, I don't know, into your calculations. That's the word. So yeah, is it a good thing? Is it a bad thing? I'm not sure, but that's up for you to decide, right? To put on your critical thinking cap. So yeah, any questions, comments about this stuff? It's a weird little concept. Have we mined Bitcoin before? Probably unsuccessfully. But here, I'm going to make this a fun little exercise for us. We're going to become computers connected to the Bitcoin network, or sorry, we're going to be connected to the Litecoin network. That's my alternative coin for this class that I've come up with. So I have a silly little example for us to play today, but I'm going to walk you through what it's like to be somebody on the Bitcoin network mining Bitcoin. So here, let's introduce Litecoin. It's got my cat as the mascot, of course, and one Litecoin. It's not worth much, but you will be able to win one. You'll be able to mine one from the next slide. You can mine one by solving a math problem the fastest, because that's really what's going on inside of the Bitcoin network. They're just solving math problems very quickly, and the first one who solves the problem gets that newly minted Bitcoin. So we're going to do the same for this Litecoin experiment. All right, so I have some slides. I have one next slide, and once I go to it, there will be 3 questions. All right, and so here's the setup. Here's a marker. Here's the whiteboard. There's 3 math problems that I'm about to give to you guys. So here's your marker. The first person to come up and write the answer, the correct answer, into the slot on the whiteboard wins a Litecoin. I'm about to draw on some napkins for you guys to have something to take home. So, good luck. Do we understand the rules of this Litecoin minting mining experience? No, just one. Just one. You should focus your efforts on one so you can be the first person on the board who writes that answer in that slot. Are you ready? Drum roll, please. Get ready to Google and get a calculator open, maybe. Thank you. All right, here are your questions. The first person, Google will probably be your the most helpful thing to you right now. But I'll create some Litecoins for you as you're working. Whee. Oh, this marker is dead. How about this one? This'll do. Oh, nice. There's a couple markers over there, so it'll be okay. As long as you round the answer to a certain number of decimal places, it's fine. As long as it's close enough. Nice. And don't give up, because maybe those answers are wrong. We're not sure yet. You got the other one too? Sorry, this marker is not the best, but you will have something to take home if you are the victor. Ooh. Did we do it? You can race. You can write it next to it. I've got my newly made Litecoins ready. Nice. Ooh, we have some different answers. Good. We'll see who wins. But this is honestly what's going on inside of your computer if you connect it to the Bitcoin network. It's just the network is giving you a math problem that involves everybody's recent transactions, and then the first computer that solves the math problem gets a Bitcoin. That's pretty much how it works. So yeah, thank you guys for playing along. That was nice of you. So hopefully that helps you understand what's going on. That's honestly all that's happening. Okay, so let's see here. Let me get the answer to number 3. I have the first 2 answers saved. So weather, Fresno, weather, San Francisco. So I see a maximum today, as far as Google is concerned, of in Fresno in Celsius, it's 32 maximum. Ooh, so it was the second answer. That's correct for that one. And then in Fahrenheit for San Francisco, the max temperature is going to be 63. Okay, yeah, so I think the first person did the current temperature. I'm sorry, but it was the max temperature. All right, so that looks good. And then here are the answers to the first 2. Let's see if we got them. They're somewhere here in the notes. Yeah. So apparently this is the answer, probably in meters per second, 1.25. Yeah, it looks right. Good. And then 385.07 in atomic mass units for the other one, and that's close enough. Depends on, I guess, the isotope that you use. But yeah, you got number 1. Very nice. Here is your mind lit coin. Congratulations. Thanks for playing. And what about number 2? Very nice. This is your 1 lit coin. Great job. And then it was this answer. So it was the 95. That was the correct one. Well done. So you successfully mined lit coins. They're not worth much, but you get lots of cred for it. You're wealthy in my gratitude. So yeah, that was fun. Any questions about cryptocurrency? Because that's pretty much what's happening. You became human cryptocurrency network nodes. Cool. So yeah, if we're good with that, I would like to switch gears to talk about another fun topic. It's called game theory. Have you heard of this word before? It's a fun little phrase. It doesn't really have to do a lot with any one subject, and so it's a nice segue after these slides on CSCI and other disciplines. This is something that has computation as the backbone a lot and is used in a wide variety of areas. So I'm excited to teach it to you. Just the first bits of it, at least. So you can learn more in plenty of different kinds of classes. There's like poli-sci uses it, finance uses it. There's like a bunch of different places. But here's the setup. Here's game theory in a nutshell. So let's pretend this is Fresno. So we've got 2 corn producers. We've got 2 people who are growing corn. Let's see, did I do this right? I just looked small for some reason. Okay, so we got 2 corn producers. And the question is, what price should these corn producers sell their goods at? So like here's somebody, they're at like the River Park Farmers Market or something. This is booth A, person A, corn grower A. Let me draw them. And they're selling their corn. And then we got person B. They're also selling corn. Competitors to one another. And so the question is, what price should these corn growers sell their corn at? Well, if one sells their corn for a very large price, like if one of them says, oh, this is $50 designer corn, and then somebody else is like, oh, this is $5 normal corn, everybody's going to go buy from the $5 person, right? So that's just natural, and game theory will tell us that. Okay, everybody's going to go the cheap one for sure. And that is going to, game theory will give us some rules. If you study it enough, it'll tell you why the prices are going to go down for that same product, assuming this was the same kind of corn. It wasn't really designer corn, it was just normal corn secretly. Like this guy's going to have to change their price to $5. All right, and that's what's going to happen. It's going to go down as far as it could possibly go down until there's an equilibrium and everyone's selling their corn at the same price, pretty much. Okay. So this is kind of what's happening when you go to a gas station. Gas prices, for the most part, are they go to an equilibrium. Okay, so that's the idea there. But that's a key keyword, and game theory has a lot of equations to tell you like when you're going to get to the equilibrium and what it's going to be. So that's kind of cool. I guess technically, game theory doesn't apply when people do illegal things. Like both of these corn growers could like get together and be like, you know what, we're the sole corn providers at this farmers market. Let's just both agree to sell our corn at $50. Like they could do that, but that is illegal, and game theory doesn't really help us there. But if they're playing fair, at least game theory tells us what's going to happen and why. So that's a cool little topic, I think, and useful. It was invented by the field itself. Was invented by a man named John Nash, a very famous mathematician. He was like his life was described in the movie A Beautiful Mind. Beautiful Mind. It's a cool movie. I encourage you to watch it. But yeah, it all started with him, and it just took off from there. A lot of different fields are using game theory to describe certain processes that are inside of them. So it's a very vague kind of thing. And so game theory is not just about like board games or video games or something like that. The definition of game as far as game theorists are concerned is completely different. Right? So a game, for game theory people, is just this. It's a strategic interaction between individuals in situations. So like people are doing stuff somehow. It's very, very vague, right? So it could just as easily talk about video games as easily as it could mention or apply to corn growers, okay? So there are different subtypes of games in game theory. There's cooperative games, which are what you expect. That's when people end up, like in a cooperative game. That means that people playing this game, in quotes, of course, because it could be something very vague, like growing corn could be a game. It could be cooperative in that people end up being better off when they work together and forming groups and alliances. Like our society, for the most part, is a cooperative game. Like I'm a teacher, I don't grow my own food, but I make money so that I can go to Trader Joe's and stuff like that. So like that's an idea. Cooperative game theory is pretty popular because it applies to a lot of things. And then there's also non-cooperative games. Interesting, where it's bad to form an alliance. So those are the ones that I don't fully understand. But like cooperative games are when people are better off working together, and groups just naturally fall out because like it makes sense. And a non-cooperative game theory is when it's either impossible to form alliances or like heavily discouraged. The only time in a non-cooperative game, if two people inside of it, and end up working together, it's like people say it's because like they're threatened or something. So that's an interesting idea. It's not a good idea to form alliances in a non-cooperative game, or it's impossible. Okay, so I'll mostly focus on cooperative games. Those are just easier to understand. They're more common. But yeah, cooperative game theory, it's all about the study of like what makes it fair. When are we going to hit this equilibrium? What's the fairest thing to do? I like that. And then non-cooperative game theory is kind of like, what's the best way to win and like put myself up top when everybody else is down below. It's a fun little idea, fun little topic, and there's plenty more where this came from if you're interested. It applies to a lot of different fields. So yeah, it's used everywhere. Game theory is all over the place. It's used in economics, just to study like how money's moving around in society, how political science to show like, all right, why candidates are more popular than others and things like that. Who's going to win, among other things. Biology, different processes are like, there's competition when you're a living cell, right? So there's just so many things that you can frame in terms of game theory, and so it's a very useful thing to study. Philosophy, and just even if you're a corn grower, game theory applies to you. So it's a very vague like definition of game, and so it works everywhere essentially. And so yeah, the reason I'm teaching you this in a computer science class is because a lot of it has to do with numbers and like computation of like what's the best strategy and making simulations and things like that. So that's a good reason to think about it in a computer science setting, because people are spending the big bucks and trying to like buy programmers time to write ways to like programs that are going to like simulate things and solve for the optimal strategy to play this game of corn production, or like trying to like get your political candidate to win, etc., etc. So plenty of money to be made, and a lot of people care. So that's kind of cool. So yeah, and the remaining time today won't be the world's longest lecture, but I want to talk about a fun idea, a fun example of a game that we can all understand, and it has a weird ending. It has a paradoxical kind of ending that we wouldn't expect. All right, so here is the game I would like to explain to you for the rest of these 3 slides, I guess. We'll solve it with game theory. It's a non-cooperative game, so that's fun. So I'll give you one non-cooperative game. It's impossible to form an alliance in this game. It's called the Prisoner's Dilemma. Have we heard of this before? It's like the most common thing to introduce when you're learning game theory, but it's a fun idea. So here's the Prisoner's Dilemma. You have 2 prisoners accused of committing a crime. They've been placed in jail in separate rooms, of course, separate interrogation rooms they're brought into, because we don't want them colluding, of course. And so it's non-cooperative immediately. Like, they can't talk to each other. It's impossible to form an alliance with the police because they're against you already. So, like, it is a non-cooperative game for sure. And the 2 prisoners in these separate rooms are given these options listed out to them on the table. Like, these are your 4 possible outcomes for how much sentencing you're going to get depending on whether or not you confess or don't confess. All right, so here is outcome 1. If prisoner A, the person in the first room, if prisoner A confesses, but prisoner B, the person in the other room, says, no, I'm innocent, but prisoner A is like, no, yeah, we did it, then here's what's going to happen. Prisoner A will walk free because they told the truth, but prisoner B, because they lied, or they were brought to lie, I guess, I don't know, maybe they were both, who knows if they're innocent or not, doesn't matter. If prisoner A confesses but prisoner B does not confess, then prisoner A is going to walk free that day, and prisoner B will get 10 years in jail. All right? That's the first option. It's the first outcome that's possible. Outcome 2 is the flip of that. If prisoner B is like, yeah, we did it, and prisoner A is like, they keep their mouth shut, then prisoner B gets to walk free, 0 years in jail. But prisoner A gets 10 years. They have to spend their time there, unfortunately. So that's interesting. And then the other 2 outcomes are also kind of nice. So outcome 3 is if they both confess, then at least they told the truth, and the judge will give them a lesser sentence because of that. Then they'll both get 5 years in prison. Okay, that's outcome 3. And then finally, outcome 4 is the best one for the prisoners, right? If neither of them confess, if they both just keep their mouth shut, all the evidence against them is circumstantial or whatever the word is, then they're all going to walk free. So if they both just keep their mouth shut, then they both get to go home today. 0 years in jail for both of them. Okay? So we can draw a grid of the options. Like here's prisoner A, what prisoner A does, and then prisoner B does. Can be on each axis. Prisoner B's outcome. And then we can draw a little grid of what's going to happen, depending on whether or not prisoner A either C for confesses or NC for does not confess, no confession. So prisoner A could either confess or not confess, and then prisoner B could either confess or not confess, right? And then we each have, they each have an amount of jail time they're going to get depending on what they did. Okay, so let's draw that out in this table here. So if they both confess, that's outcome 3, then they're both getting 5 years in jail. If B confesses, they're getting 0 years. When A does not confess, they get the 10. So these are the worst diagonals, right? So if B does not confess, but A does confess, that's outcome 1. And so A gets 0 years and B gets 10 years. That sucks. And then if neither of them confess, if they just can both keep their mouth shut in these separate interrogation rooms, then they can both walk free today with 0 years of jail time. So the question, of course, is what should these prisoners do? What is the optimal outcome for them? Do we have any thoughts? I see one that would be the greatest thing ever, right? Yeah, the best thing for them would be to not confess, you'd think, right? If they both don't confess, then they can both walk away. But this is a non-cooperative game, and those 2 prisoners can't trust each other. And so though this looks the best, this is the optimal outcome for them, it's not really the optimal outcome if we think about it long enough. And I'll show you some math to prove that in just a second. So this looks like the optimal outcome from our perspective, of course. But actually, it's not going to be the equilibrium. It's not going to be what happens. It's not the best thing for the prisoners. Let me show that to you. All right, so what we're trying to do, named after John Nash, is calculate a Nash equilibrium. Right, it's a number. It's the, well, in our case, it's a number at least. It's the optimal solution to this prisoner's dilemma problem. It's going to be, we're going to look for what is the Nash equilibrium for this problem. And that is one game theoretic way of solving it that tells us why it's going to happen the way it happens. All right, so all a Nash equilibrium is, it's a set of strategies. It's a way to play the game for each player that has this property, has the property that each player's choice is their best response to the choices of the other players. So it's kind of, a Nash equilibrium is all about like non-cooperation. It's the best response to the choices of the other players. Even if they do something horrible, you're like hedging your bets. That's kind of the idea of a Nash equilibrium. It's all about playing it safe. So the key idea, and what we're going to discover about this, is that it's not good for the prisoners to both do this. It's a bad idea because prisoner A does not know what prisoner B is going to do. So they both have to play it safe. Does that make sense? Because they don't trust each other, they're both criminals after all, they have to play it safe. And the Nash equilibrium is kind of the mathematical way that made this dude famous, and it's just a mathematical formalization of the idea of playing it safe. Okay? So another definition, another easy to understand example of a Nash equilibrium is this kind of quote that I stole from the internet. It's Nash equilibrium is kind of like a law that nobody would want to break, even if there was no punishment for breaking it. So, for example, a stoplight is a Nash equilibrium experiment, more or less. Like a stoplight, right? When a stoplight is red, we all obey it, right? For the most part. We're all going to stop at a red stoplight, aren't we? Why?
You run there, you can get hit.
Yeah, that's pretty much right. Like you could, most likely there is not a cop at that intersection. Like you could run that light if you really wanted to most times, right? But we don't because we value our lives. Yeah, we don't want to get hit. And we assume like everybody else is playing the game and like it's optimal for them to also play that game of stopping at the stoplights. We all agree. So it's like a self-enforcing law. That's what a Nash equilibrium is kind of all about. So we're going to find one of those for this prisoner's dilemma experiment game. And so for the prisoners, the way that you calculate this Nash equilibrium is to go and calculate, like, for every option, I only have control over what I do. Like, you consider it from the perspective of one of the prisoners, because it's a symmetric problem for each of them. You consider, like, what's the average sentence for me if I confess, and what's the average sentence for me if I don't confess, regardless of what the other person does. Like, average it over all the other possibilities for what the other guy's going to do, because I don't have control over that. Right? So we're going to do that on the next slide. So it's symmetric for both of these prisoners. So, like, we can just consider it from, like, prisoner A's point of view, for example. Let's draw that. Let me show you what I mean by that. Did I get just what I wanted? Yes. Paste. So here's the grid again. And the idea is what we're going to do is we're going to consider this from, let's say, prisoner A's perspective, because it doesn't matter. Like it's symmetric. Like it's 0 or 10, 10 or 0. It's like it's flipped along the diagonal. It's not a big deal. So let's consider this from prisoner A's perspective. And what we're going to do is we're going to calculate the average sentence for prisoner A. For some reason, there it goes. We're going to calculate the average sentence for prisoner A, right? If they confess or if they don't confess. Prisoner A, boop. So if they confess, what do they get? And if they don't confess? If they don't confess, if they keep their mouth shut. Boop. So there. And then what we're going to do is we're going to calculate the average time spent in jail for doing that, for confessing or for not confessing. Average time spent in jail. So there we go. All right, so if prisoner A confesses, that means we're in this column of the box, right? Prisoner A has no control over prisoner B. So it's either going to be like this is the outcome or this is the outcome if prisoner A confesses, right? It's either one of these two outcomes. Do you see that? And we have no control. If we're prisoner A, we have no control over what the other guy's going to do. If they confess or they don't confess. Maybe it looks nice to confess for them. I'm not sure. So if the prisoner A confesses, what happens to them, right? Because they're in one of these two cases. We're not sure. But on average, what's going to happen to prisoner A? It's either, like it was this case where they get 5 years, or it's this case where they get 0 years. You see that? So on average, for prisoner A, the average time spent in jail is 5 plus 0 over 2, right? It's an average of two things. So that's 2.5 years on average in jail if prisoner A confesses. Do we see that? So they have no control over what prisoner B is going to do. No control at all. It's a non-cooperative game. So that's that outcome. And then if prisoner A doesn't confess, that means they're in one of these two outcomes, where they end up being in jail for 10 years or 0 years. They have no control over what the other guy's going to do. So just on average, what's going to happen? Either they're in jail for 10 years or they're in jail for 0 years. On average, if they don't confess, they're going to spend 5 years in jail. Do you see that? And so, what's the optimal outcome for prisoner A and then also for prisoner B, because it's a symmetric game? Of course, it's this one. Because we have no control over what the other guy's going to do. We just want to limit our jail time, of course. So we're going to pick to confess always. Both prisoners, they should both confess. Do you see that? We should pick this outcome. That is our equilibrium. It's not this one, which is counterintuitive. You'd just be like, if they could trust each other and both keep their mouths shut, it would work out, but they have no control. Because they have no control, on average, it makes more sense to confess, and that's the Nash equilibrium. That's what these prisoners are going to do. They are going to both confess. That is the best way to play this game for them. You see that? Which seems very paradoxical. If they could just keep their mouths shut, it would be fine, but it makes so much sense under the lens of game theory. It's like, we can't trust this other person. Let's just figure out what our options are. And so they're going to pick the way that limits. Like, they're going to do what they can do because they don't have any control. They only have control over themselves. They're going to do what they can do to minimize their amount of time in jail. And so that's why the optimal outcome for the prisoner's dilemma, the Nash equilibrium, is for both prisoners to confess. Isn't that cool? It's a fun little idea. It seems paradoxical, but it makes all the sense in the world thanks to game theory. And that is the point of the field. So, yeah, any questions about that? That's the prisoner's dilemma. It is just like the quintessential example when you're learning game theory. That's the first one I'll show you. So yeah, if we are happy, I think that's all that I wanted to talk about today. So yeah, no new assignments. You got plenty to do that I assigned last week. Next time we'll have a programming lecture, and I will talk about the final as well. But that'll be on Wednesday. Okay. So the rest of the time is all yours to work and ask questions.